Thank you for the organizer. My talk is kind of the final objective is to prove the Hilbert Nullstellensatz that belongs to the cornerstone of the algebraic geometry. But here we use a very different way to prove it. We use model theory to prove it. The model theory is also new to me. I know some people here are expert in the model theory, like Sergio, I believe. So, so correct me if I'm wrong. Okay. So this is kind of a mini talk I've already given. To give a very brief introduction to the model theory. So first, let me introduce briefly what Hilbert's Nullstellensatz is. So here, K is an algebraically closed field, okay? We have an ideal, a non-zero ideal in this polynomial ring. And we define Vi, which means the zero set for all polynomials in this ideal. Okay, so that's called Vi. And we can also define in the opposite way, given a subset, I mean non-empty subset, okay, in Kn, we define IV, ideal from the subset, which means that makes that if we plug in all elements in V, all these polynomials will be equal to 0. This gives us a set. Okay, actually, this is an ideal. It can be proved. And Hilbert's Nullstellensatz tells us, okay, if we do these two operations, IVI will be a radical ideal of the original given ideal I. And certainly, it has another form. So Vi is not empty. That means for any number of polynomials, okay, as long as the ideal is not the ideal generated by this polynomials is not the ring itself, then we can always find a common roots for this set of polynomials. Okay. Here, because of Hilbert basis theorem, so any ideal in a polynomial ring is finitely generated. So that means we only need to test for finitely number of polynomials, because I is always finitely generated. Okay. Here, these two theorems, these two versions are equivalent. Okay, are equivalent. Let me briefly give the proof of why they are equivalent. Okay, so suppose IVI is a radical of I. Okay, and if Vi is empty set, that means that there's no common set of roots, and then IVI will be I empty, okay, I of an empty set. That will be the ring, the order ring itself. Okay, but the square root I is not equal to K square root I. I mean the radical of any ideal, non-trivial ideal, is not equal to the ring itself, because otherwise 1 will belong to I, which means I itself is the entire ring, which is not the definition of an ideal. So one direction is proved, okay? And for the other direction, suppose Vi is not empty, okay? Then we know this polynomial ring is a Noetherian ring, so that means it is finitely generated. I mean, every ideal is finitely generated, okay, say by this M polynomials, okay? And we want to prove that IVI is a radical ideal of I. So suppose we find the polynomial in G. Suppose we have a polynomial G. The G vanishes if all Fi vanish. Okay, that means in G also share the common roots for all Fi's. Okay, and then we introduce an extra variable x0, then 1 minus x0 G and sorry, Fm. Okay, Fm cannot vanish at the same time. Okay, certainly because it is obvious because if G vanishes, then we have 1 minus x0 G doesn't vanish. Okay, so we can't make them vanish at the same time. So if we add an extra variable x0, then we have a new polynomial ring. It is also a Noetherian ring from the Hilbert basis theorem. Okay, then we can say we can find some number b0, b1, b2, and up to bn. So the linear combination is equal to 1. Okay. Okay, for some b0, b1, bn in this new polynomial ring. Okay, because they don't vanish at the same time. Okay, that means the ideal generated by these polynomials must be equal to 1. Okay, must be equal to the entire ring. Okay. So this is true for any equal to 1 is true for any like for any value for x0. So we take x0 is 1 over G because G is not equal to 0. Okay, and then after we clear the b0 part and we have this part, now we can get this ratio equal to 1. Okay, for some r greater than 0. Okay, and that means GR is in I because h1 f1 plus up to hn fn belongs to I, so that means GR belongs to I. But this is exactly the definition of a radical ideal. So that means G belongs to the radical ideal of I. Okay, so that means the two theorems, the two versions of Hilbert's Nullstellensatz are equivalent. Okay. So in today's lecture, I'm going to prove this version. Vi is not an empty set. Okay, using the model theory. But when I give the lecture, my purpose is to introduce model theory by proving the Hilbert's Nullstellensatz. So some parts, okay, may be not relevant, closely relevant to the proof, but if time permits, I'm going to introduce that part. Okay. Okay. As every branch of mathematics, we start from sets. Okay, so let E be a set. Okay, then we define an n-ary relation R, which is a subset of En for n integer. So given n integer, n greater than or equal to 0. So a subset of En is called a relation. Okay, n-ary relation. Okay, then we can talk about isomorphism, and E is called the universe, okay, of the relation. Okay, then if we have two relations from two different universes, anyway, we can define an isomorphism. That means a bijection between E and E prime, such that we can induce a bijection from the two relations from R to R prime. Okay, so that means a bijection from E to E prime in that which induces a bijection between R and R prime. Okay.
Sorry, I have a question. Can I ask?
Yeah.
So R is a subset of. Sorry, I can't hear myself.
R is a subset of En.
Okay. Yeah. So now I have a problem because I can't hear myself, so it would be very hard to.
Okay.
Yeah.
So, can you see now?
No, I'm just saying that since I can hear myself, would echo my voice.
So
maybe you should use your headphone or something. Anyway.
Really?
No, it's okay. It's okay now. Okay.
It's okay now.
So, yeah, it's good. So R is a subset of En.
Yes.
This map bijection S is between E and E prime. So then what do you mean by S of A? A is a subset of En.
A is element in R. In R.
But R is a subset.
Prime and R has the same N. So we have every element in R and R prime has the same number of components.
Okay, so both R and R prime are a subset of En for the same N?
Yeah, same N.
Okay.
Same N. Okay.
Okay, thank you.
Yeah. So now it makes sense. Yeah.
So you're talking about, yeah, so it's just a map between the Cartesian products.
No,
En and E prime.
It's from E to E prime.
That maps R to R prime.
Yeah, that's
okay.
That uses a map from R to R prime.
Yeah. Now, so the notation with the quotients there, it's not. There's no actual quotient, right?
No, it's not a quotient.
Okay.
That means, yeah, R is R comes from E.
Okay. Yeah. Okay. No problem.
Yeah. So it's not a quotient because everything is a set. Okay. So we don't have any quotient. Okay. So E is called the universe of the relation. Okay. Certainly, we can also introduce the restriction. So here, let's say E prime is a proper subset of E, and then we can restrict our R to the universe of E prime. Okay. Then we can get a new relation under E prime. This is called restriction of R to our new universe, a smaller universe E prime. Okay, so that gives us a restriction of the given relation. Certainly, we can also say E is an extension of E prime, or R, extension of the, E is an extension of E prime, which means the corresponding relation is an extension. Okay, depending on which direction we talk about these two relations. And we also talk about cardinality of the relation. It's not how many relations, how many elements in R, but it's about how many elements in E. Okay, that is the cardinality of the relation. Okay, it is some kind of against our common sense. Okay, opposite to our common sense. Okay, okay. So we say a relation is finite if its universe is finite. Okay, yeah, maybe the number of elements in a relation may be infinite, but its underlying universe is finite. Then we still say this relation is finite. Okay. Okay. Then we comes with a very important definition. This definition, for me, it's kind of a mimic of the local global principle. Okay, so here we define local isomorphism. Okay, so that means we we have an isomorphism between a finite restriction of R to a finite restriction of R prime. This finite restriction gives us a local isomorphism. It gives us an isomorphism that is called a local isomorphism. Okay, it's not a global isomorphism, but it is a local isomorphism. Like in schemes, if we can group all the local isomorphism, we are going to build up a global isomorphism in some sense. Okay, so this is kind of a reminiscent or of the local global principle. Okay, and this set is denoted by. I think this is standard notation in model theory. We use S0 R prime. It's called the set of local isomorphisms, and it is very important fact. Empty set belongs to this local isomorphism. Okay, yeah, certainly. If the universe becomes empty, then relation becomes also empty. So there's isomorphism between empty set to empty set. Okay.
Sorry to interrupt. Would it be fine if I, just ask a question, or I should raise my hand to ask a question?
Because no,
okay,
it's not a class, so you can ask me question at any time. You don't need to raise up your hands. Yeah.
Okay. So here, E and E prime are two separate sets, or E prime is a subset of E?
No. E and E prime are independent.
Okay, so E and R prime are independent.
Yeah.
So this isomorphism, is it isomorphism as a universe to universe? So there is a map also from R prime to. Because you haven't defined isomorphism. You have defined
both. First, we find a subset from E and a subset from E prime. Okay. This is a restriction from the two universes. Then from this restriction of the two universes, we find restrictions for the two relations.
But when you define restriction, E prime was subset of E, but you're saying that E and E prime are independent.
No. Here.
Can you go back to the definition of restriction, please?
Yeah, restrictions here.
So prime is subset of E, no?
Yeah, subset of yes.
So then, in your definition of local isomorphism, E prime is a subset of E.
Yeah, no.
I think he is just using the same letter for different things.
Yes. We use the same letters for different meanings. Okay. Here, E and E prime are two different independent universes. Okay. Then we find the. So I don't know if I can write something. So what I'm saying is, let me see if I can write. Okay. Okay, so what I'm saying is, so you have, what I'm saying is, so we have E. Sorry, I have some trouble using my Wacom.
Okay, so, it's fine.
Yeah, so E1 belongs to E. Okay. And this is a restriction. And then we have another restriction. E1 prime belongs to E prime.
Okay.
Okay. Then we find a bijection between E1 and E1 prime.
Okay.
And this bijection induces a bijection from the restriction of the relation, the two relations. Okay.
So you're saying that a local isomorphism is a map from E to E prime with this property that when you restrict it to finite to subset is going to be isomorphism.
No, we don't care about. First, we take the restriction, then to see if we can find an isomorphism.
Okay. Thank you.
Not like not from the map between E and E prime. Maybe we don't have any map from E to E prime, but when we have some restriction, then we find the bijection. Okay.
Yeah. Thank you.
Okay, let me close it. Okay. Okay. Now, the important observation is empty set is in the set of local isomorphisms, because it is natural that empty set there's one unique isomorphism. Okay, certainly it is possible that the only local isomorphism is the empty set. Okay, yeah, it is possible. For example, one relation is a reflexive binary relation, and the other one is anti-reflexible relation. Then the local isomorphism will be the empty set. Okay. So then, starting with this S0, okay, we can inductively define P isomorphisms. So when we say isomorphisms here, we always mean local isomorphisms between R and R prime for any P, for any natural number P. Okay, and because we've already defined S0, so if we know the definition up to SP, then the local isomorphism in SP plus 1, okay, will be must satisfy the two conditions. So this is this is called the back and forth condition. So this is the forward condition. So for any element in the domain, which means the E, okay, we can find a local isomorphism from P, okay, which is the extension of S, and this T is defined at A. Okay, that means T is the extension of S, and T, the domain of T contains the new element A for any A. And this is back condition. Okay, suppose we have a new for any element B in the image E prime, then we can find a local isomorphism in SP. The image of T contains B. Okay, so that means if we keep adding elements either from the domain or in the image, we can always find a local isomorphism from the previous P isomorphism. Okay, contains the new element. Okay, either from image or from the domain. Okay.
So,
yeah.
Oh, actually, I was going to ask this.
Okay, so that means we have this relationship. Okay, for this local isomorphisms. Okay, actually it will stop somewhere. Okay, but the most important part is this. Okay, we define intersect. We define the intersection of all P local isomorphisms. Okay, and we introduce a new symbol S omega. Okay, for model theorists, I believe everybody knows what omega means. That means the first countable ordinal, right?
I think I have a question still.
Yeah.
Do you mind going back to the previous slide?
This one, yeah.
So the little s in SP plus 1.
Yes.
What kind of object is it?
And this is the local isomorphism for the two relations, R to R prime.
But isn't that the definition of isn't that the definition of S0? Like S0 contains.
Yes. This one belongs to S0, but it satisfies more requirements. Okay. This one and two are the requirements, actual requirements.
That there is an extension.
Yeah. Yes.
Ah, okay. Now I understand. Yeah.
So,
Thank you.
Yeah. It belongs to S0, but it satisfies more more requirements. Okay.
Thank you.
So that's why we have this kind of containment. Okay. So when we do the intersection of all these local isomorphisms, then we got a new set S omega. An element in this S omega is called an omega isomorphism or elementary local isomorphism. Okay, this is a very important concept in model theory. Okay, because this will give us local global principle. Okay, and that means if it satisfies locally, like in the quadratic polynomials, right? If it has solution for any prime number p, then it has solution in Q, right? So a modulo p, yeah, modulo p. Okay, so that's kind of a local global principle here. So here, if empty set is an elementary local isomorphism, okay, excuse me, it's a typo. R and R prime, not F prime, sorry. R and R prime are elementary equivalent, we say, okay, and denoted by this one, okay. And that means we can, from the empty set, we can keep throwing elements, okay, in the empty set, and we can still get a local isomorphism. Okay, so that means we can start from nothing, and then we can build up our local isomorphism with more and more elements. Okay. So, and another important concept is if we have any tuple coming from E, belongs to E is abusive. It should be E to the power n. N is the how many components arity of this vector. Okay, but here I just use E, meaning all the components come from E. Okay, and B in E prime. If the natural, so here A and B have the same arity, so same number of components. If the natural mapping from A to B gives us an element in SP, then we say A and B are P equivalent. Okay, and okay, denoted by this. Okay, and if this map gives a local isomorphism for any P, then we say these two tuples are omega equivalent or have the same type. Okay, same type, denoted by this. Okay, from that we have another more important concept, elementary embedding. Okay, this actually gives us what we are going to need, improve Hilbert's Nullstellensatz. Okay, so the extension R to R prime is elementary if this A to A. So if A belongs to R, certainly A. Sorry, if A belongs to the universe of E, certainly A also belongs to the universe of R prime, because it is the extension. Okay, and then if this identity map from A to A induces a elementary isomorphism, then we say the extension is elementary. It's elementary. Okay. For any A from E. Okay. Certainly follow this idea. For any ordinal number alpha, we can define S alpha R prime. We just keep intersecting the local isomorphisms. Okay. And we can also intersect all such S alpha for all ordinal numbers alpha. Then we define S infinity. Okay. And yeah, so that's a very basic, important concepts. Okay. Yeah. the most important concept is elementary. Okay, elementary embedding or elementary extension. From there, we can prove the Hilbert's Nullstellensatz. But still, we need other tools. Okay, it's still a long way to get there. Okay. Now here comes with the formulas. Okay, formulas. They are defined inductively. So complexity 0 means x1 equal to x2 or a relation. Okay? An equal or a relation that gives us the basic formulas of complexity 0. Okay. Now, if we have defined the formulas of complexity up to n, then the formulas of a complexity n plus 1 are this negation of f. Okay. There exists x for any x, okay, or f and g or f or g, okay, and f and g, at least one of them has complexity n, okay, yeah. Okay, so that's the formulas, okay. Now we define, okay, sorry. Now we define what this notation means. Okay, so we say FA, sorry, it's not a line, but it's an arrow, right arrow. Okay, so we say FA satisfies the relation R. Okay, if this A replaces the free variables, and FA is satisfied in R. That means FA is an element in the relation R. Okay. So this is what this notation means. Okay. Now we say F and G, the two formulas are equivalent. Yeah. If FA satisfies R, if and only if GA is satisfied in R for any relation R and any n-tuple A. Okay. For example, for any for this symbol any can be replaced is equivalent to not there exists not. Okay. So that's an example. That is an example. Okay. So now here is what a sentence means. A sentence means a formula not having free variables. Okay. That means all variables are bounded by there exists or any. Okay. So this is called a sentence. But certainly there's the opposite one. Another extreme is a quantifier-free formula. Okay, that means f doesn't have any quantifiers. That means f doesn't have there exists or any. Okay, these two symbols. Okay. Now here is called a free set theorem. Okay, so let's say R and S are two M-level relations. Okay, R and S are elementary equivalent if and only if they satisfy the same sentences. Okay, so it is narrowed down to sentences instead of arbitrary formulas. Okay, and the number two is more important. So S to R is an elementary embedding if and only if any n-tuple from S satisfies same sentences as considered from R. So that means if it is elementary embedding, we don't distinguish. Okay, the n-tuples come from S. If n-tuple comes from S, we don't distinguish it comes from S or comes from R. It comes from R. Okay. So how to how to prove the Hilbert's Nullstellensatz, we use this elementary embedding. So first we prove, okay, the set of polynomials have solution in an algebraic extension of the base field. Okay, then using the elementary embedding, we prove it has a solution in the algebraically closed field of the base field. Okay, so that's the idea. That's the idea. Okay. Okay. Now we go to the models. Okay, a relation R is called a model of a sentence F if F is satisfied in R. Okay. Okay. And similar for a set A of sentences, not just one sentence, maybe many sentences. Okay, then we can also define a model for the set of sentences. So if A has a model, we say A is consistent. Okay. So then we can define consequence of a set of sentences. That means if A is satisfied by a model, then the F is also satisfied by that model. Okay, then F is called the consequence of A. And then we can introduce theory. A theory is a consistent set of sentences containing all its own sequences. So it's a closure of a set of sentences. Okay. So if the closure is a maximum, then we call it a complete theory. Okay, complete theory. And certainly every theory T is contained in a complete theory. Okay. So in fact, we can take a model M of a theory T, which is maybe not complete. Then we take set Tm of all sentences satisfied by M, and it can be proved this set Tm is a complete theory. Okay. Yeah. So this is a very important observation in the model theory. A theory T is complete if and only if any two models of T are elementary equivalent, okay, which means they satisfy the same sentences. Okay, so that means they are elementary equivalent, the two models. Okay, yeah. Then the Tarski's test. Okay, this is the this is stone to prove. This is a cornerstone to prove the Hilbert's Nullstellensatz. Okay, so this is R prime, E prime, not S. Okay, it's an elementary embedding if and only if. Okay, for any like a vector from E of R and any formula f x y. Okay, if this formula, this sentence is satisfied in S, okay, then it is satisfied in R. Okay. If the vector A comes from R, okay, the smaller relation R. Okay. So this is our cornerstone to prove the Nullstellensatz. Okay. Actually, it is a very easy consequence of the of this Tarski's test. Okay. Now, so far we talked about just one single relation, but all this can be transformed into multiple relations. Okay, certainly we fix a universe. Okay, universe, and certainly every relation has its own arity. So the set of arities, all arities, the set is called the signature or the similar type of the multi-relations. Okay, actually, you can see relations also include functions, right? Also include functions. Okay, but anyway, we will single out functions from the relations. Okay, so now fix a similarity type sigma. Okay, suppose we have a constant symbols, Ci, constant symbols, and the function symbols, Fj, the arity is Mj, and the relation symbols are K. Okay, and now we can define structure S. Okay, of sigma in the universe, E is assignment. So that means we are going to assign all the symbols to something coming from E. Okay, so every Ci is assigned an element in E, and any function symbol is assigned as a map, okay, from EMJ to E, okay, depending on the arity of the function, and also a relation. A relation is a subset of EMK, okay, depending on the arity of the relation symbol. Okay. Now we can talk about the formulas in this multi-relations. Okay, so first we define the terms of complexity 0 are variables and constants. Okay, so this is the simplest terms, and then we define inductively the terms of complexity up to complexity of any number n. Okay, so terms of complexity n+1 are this, okay, where f is function symbol of arity m, and the t1 up to tm have complexity at most n, but one of them has to have complexity n. Okay, so this is terms. Then we define formulas. Okay, atomic formulas, which means that they have complexity 0. That means equal or a relation. Okay, T1 equal to T2 or relation. Okay, similar, very similar. Okay, to a single relation. So if we have n, then n+1 formulas of complexity n+1 is negation of f. Okay, and there exists or for all, and or all. Okay, so very similar, very similar. Okay. So now we define two structures are elementary if they satisfy the same formulas. Okay, this comes from the single relation. Okay, a single relation. Okay, and extension is elementary. Okay, if every tuple from a small structure satisfy the same formulas as in the large structure. Okay, so that means elementary means the tuple. We don't care about where the tuple comes from. Okay, comes from. Okay. So now fix the language L to a signature L. Sigma language L is a language means this constant symbols, the function, the relations. Okay, that's called a language. Okay, language. Okay. So fix a language L to a signature L, signature sigma. Then for any sentence F, we define that. Okay, we define that. T, F belongs to T, and T is complete. It's complete theory. Okay, maybe I should go faster. Okay, so this gives us a topology. Okay, for the set of complete theories. Okay, it turns out this topology is the Hausdorff compact topological space. Okay, so T is Hausdorff compact space. Okay, so this has a very important consequence. Okay, that means any set A of sentences is consistent if and only if any finite subset of A is consistent. Okay, this is very useful. Okay, because finite is always better than infinite. Okay, in most cases. Okay, and if like from A, from the set of sentences A, we can induce F, we can prove F, then we can always find a finite subset A prime, such that from A prime we can prove F. So that means we don't need infinitely many facts to prove another fact. We always need finitely many facts to prove another fact. Okay, because of this compactness. Okay. Okay. Then we go to types. Okay, we go to types. Okay, so we fix the language L. Okay. Okay, so two elements, A and B, in two L structures, maybe for the same language L, we can attach different structures, right? So two elements, A and B, in two L structures have the same type if they satisfy the same formula. Okay, that means they are equivalent. Okay, same type means equivalent because they satisfy the same formulas. Okay. The type of element A is the set PA of fx satisfied by A. Okay, so all sentences that A satisfies is called the type of A. Okay, the type of A. All these are very important concepts in model theory. Okay. Then we go to S0 of zero type. S0, zero type is just what we've seen. The space T of complete theories. So this is a compact Hausdorff space. Okay, just the set of all complete theories. But S1 is different. S1 is the most important type. The space of complete theory in L. Okay, besides L, we add another constant symbol X. Okay, the space of these complete theories, S1. Okay, and certainly S1 is also a compact Hausdorff space. Okay. Okay, and then we can define S1T. T is a theory, not necessarily complete. Then S1T is a set of T types in models of T. That means all complete theories in L and X, but containing T. Okay. Containing T, okay, the fixed theory T. Okay, so S1T is a subset of S0. S1T is a subset of S. Here, S1T is a subset of S1. S1. Okay. Okay. Then we go further. Okay. If T is complete theory now, if T is complete theory, and M is a model of this complete theory. So because T is a complete theory, then any model, any two models for theory will be elementary equivalent. That means they will satisfy the same formulas. Okay, so that means it doesn't matter which model we choose, okay, because they are elementary equivalent. Okay, and we pick up a subset A of M. Okay, so define TA be the set of sentences in the language L, and the union the new constant symbols from the subset A that are true in M. Okay, so which means M is a model of the sentences in the language L and A. Okay. Now we define S1TA or symbol S1A if T is clear, okay, to be the set of complete theories in the language L, union A, union this constant symbol X containing TA. So TA is a subset of the complete theory in S1A. Okay. Now, if P is in S1A, we say P is realized in M because here there's only one undefined constant symbol X. So if we say P is realized in M if we have M in capital M with type P. That means if we replace this X with the small m, okay, all sentences in P will be satisfied in M. then we say P is realized in the capital M, in the model M. Okay. Now we say this model M is omega saturated. Then omega saturated, that means for any finite A, vector A in M, and for every type in S1A, this type is realized in M. That means for every type, we can always find an element in M that satisfy all sentences in the type. Okay, corresponding to Nullstellensatz, that means we can find a common element that satisfies all polynomials in this ideal. Okay, so that's the relationship between the model theory and the Nullstellensatz. Okay. A basic fact is every structure has an omega saturated or elementary extension. This is also very important in Nullstellensatz. So in the sense that every field can be embedded elementary, has elementary embedding into an omega saturated algebraically closed field. Okay. Then, because it is omega saturated, then for any set of polynomials, we can find, because it can be realized in M, that means we can find a common solution. Okay, so this is what it means. Okay. Okay. Now here's the theorem, which is another important component in the proof of the Nullstellensatz. Okay, so let T be a theory. Certainly, we don't require it is complete in a given language L. So in a given signature and symbols. Define F to be a set of formulas having free variables. Free variables means they are not bounded by their exists, and for any. Okay. So such that for any two tuples from models of T, n is greater than 0, have the same type, which means they satisfy the same formulas if and only if they satisfy the same formulas in F. Okay. So that means if we satisfy the smaller subset, then they satisfy the same formulas for any formulas. Okay, for any formula. Okay. So that means the two tuples are good in the small set of formulas. They are good in the bigger set of formulas. Okay. Then, the theory is for every formula Gx, there exists Hx, which is a Boolean combination of elements in the smaller subset of the formulas F, such that Hx and Hx, Gx and Hx are equivalent. Excuse me, Gx and Hx are equivalent. Okay, under the language L. Okay, and for any model of T. Okay, for any model of T. Okay. This is important in the sense that if F is the subset of a quantifier-free formula, okay, then we say T admits quantifier elimination because here Gx, maybe Gx has some quantifiers, but Hx, if we choose F is a subset of quantifier-free formulas, then Hx doesn't have any quantifiers. So that means Hx is a quantifier-free formulas. Okay, and Gx is equivalent to Hx, which means Gx is equivalent to a quantifier-free formulas. So that's why we say T, the theory T admits quantifier elimination. Okay. Then we have another concept definition, we say a theory T, not necessarily complete. It's a model complete. Maybe it's not complete, but we say it is model complete if whenever we have two models of T and M is a subset of M. Okay, certainly it has an embedding, but here we say it is a model complete if the embedding is elementary. Okay, it's elementary. Okay, yeah. Certainly we have more definitions in this part. For example, model companion, model completion, and companions. Okay, they are related with the relationships of models. Okay, but this is what we need. This is what we need. So an important factor is if T admits quantified elimination, T is model complete. So that means if we have two models and one is included in another, then this inclusion is an elementary embedding. Okay. So that means if we have two algebraically closed fields, okay, for the language of fields, and one is included in another, then this inclusion is an elementary embedding. So that means we can find a common solution. Okay, yeah. So we can see this. Okay, we can see this. Okay. Now we go to the fields. Okay, the language of fields. Okay. So we discuss fields under this language. We have two constant symbols, 0 and 1. Okay, minus is not a subtraction; it means negation. So 3 goes to this is minus means a unary operation. So for example, 1 goes to -1. It doesn't mean 2 minus 1. It means 2 goes to -2, 1 goes to -1, etc. And the plus and the multiplication have the normal meaning. They are binary operations. Okay, so from here we can define inverse. Okay, and we can define, yeah, we can define inverse. Okay, and certainly here an atomic formula is Px equal to Qx, right? P is a polynomial. Multiplication, multiplication, addition, and negation. Okay, so Px equal to Qx. Okay, for some polynomials P and Q. Okay, for our convenience, we bring Qx over to the left-hand side. Then we have one single polynomial Px equal to 0. Okay, and that's our starting point to prove a Nullstellensatz, right? So equal to 0 in Nullstellensatz means an atomic formula, okay, in the language of the closed fields of the fields. Okay. So for the characteristic of a field, we need the formula P equal to 0 for some prime number P, okay, or the negation of P equal to 0 for any prime number P. So that means for characteristic 0, then we need infinitely many formulas. Okay, so remember, so all these formulas are quantifier-free formulas. Okay, P equal to 0 or negation P equal to 0. Okay, so combining together, and also for algebraical closeness, okay, we need the following set of axioms. Set means for any n. Okay, for any n. So for any is 0 up to an minus 1, there is x, the polynomial equal to 0. Okay, that means algebraically closed. Okay. Okay. Now here comes with the theorem. Now the theory of algebraically closed fields admits quantifier elimination. So that implies, okay, the theory is model complete. Okay, and the theory of algebraically closed fields of a given characteristic is complete. If it's not a given characteristic, it's not complete. But with a given characteristic, it is complete. Okay. Here, the proof of completeness, I don't have time. I prepared the proof. Okay. One, it is a mini talk, but here I didn't give because of the time. Okay. So, so here the proof of completeness uses the wash-out test, saying that if a theory T is kappa categorical for some infinite cardinality K, the categorical means if the theory T has a model M with cardinality kappa, then that model is unique. If that model is unique up to isomorphism, then we say the theorem T is kappa categorical. Categorical means unique up to isomorphism under this cardinality. Okay, and if the theory has no finite models, then it is a complete theory. This is true because any algebraically closed field is infinite, right? We don't have a finite algebraically closed field. And the kappa categorical, let me say, for like uncountable cardinality, okay, the two fields are isomorphic. Two algebraically closed fields are isomorphic if and only if, okay, I mean, suppose their cardinality is uncountable, then they are isomorphic if and only if they have the same characteristic and they have the same isomorphic transcendental basis. Okay. But we can always find an algebraically closed fields with uncountable cardinality. Okay, and no matter what the characteristic is. Okay. Yeah. So here, the theory of algebraically closed fields is complete if the characteristic is given. If it is not given, it's not complete. Okay. Now here is Nullstellensatz. Okay. Let K be a field, and if a set S of equations in K, this polynomial ring has a solution in any field extension, capital K over small k, then S has a solution in any algebraically closed extension L of K. Okay. That basically that's Nullstellensatz, right? I'm going to explain if it's not clear. Now we prove this version. Okay, and so here we have K and U, a big K and a big U. So we make a extension, a field extension K1 over K and L, and we require K1 and be an algebraically closed field extension. Okay, this is doable, right? Certainly we could do that. Okay, we could do that. Okay, and then we have because our assumption is a set S has solution in capital K. Certainly, it has solution in capital K1. Okay, in big K1, because K is subset of K1. So this is true. The K1 is the model of this sentence. Okay, that is X, Sx is true. Okay, yeah, Sx equal to 0. Okay. And on the other hand, remember Sx has parameter in K, small k. Okay, but K is in L. Okay, L is an extension of K. Okay, certainly Sx has parameters in the capital L. I mean all coefficients. Parameters means all coefficients come from small k or come from small l. Sorry, big L. Okay. Then theory T is algebraic closed fields admits quantifier elimination from the previous theorem, so it is model complete. Okay. Then we know L and K1 both are algebraically closed, so they are model of the theory. They are the model of the algebraically closed field theory. Okay, so L and K1 are model of T, and L is a subset of K1. So that means L embedding K1 is an elementary embedding. Okay. Now we know K1 is a model of this sentence, is a model of sentence. Okay. And all parameters of Sx are in L. They are in L. Okay. So from the Tarski's test, we know this is also satisfied in L. That means we can find a solution in L. Okay. So why this is the Hilbert Nullstellensatz? So that means for a set of equations in this polynomial ring, we can always find a solution in a field extension, right? So if we don't put restriction on this on what the field extension is, right? For example, every irreducible polynomial corresponds to a prime ideal, and if we modulo the prime ideal, we get an integral domain, right? And the integral domain can be embedded into a field, and this field has a solution for that ideal, right? So then this ideal has solution in the algebraically in the algebraically closure of the original field. Okay, so that's the Nullstellensatz. Okay, so this is a very interesting approach. Okay, so we can see how the model theory helps number theories. Okay, yeah. So that is my presentation, and thank you. Any questions?
Maybe Mohammed?
No, I don't. I could follow to some point, but then I kind of lost.
Okay. Yeah.
Sorry, I thought. Oh, Fernak is raising her hand.
I have one question. What is why is it called Nullstellensatz? What's the name? The reason for choosing that name for the theorem?
Sorry, Franak.
The Nullstellensatz. What is the? Why is it called Nullstellensatz? What's the reason for that?
Nullstellensatz comes from the Germany. So Satz means theorem. Satz. Null means zero. So zero set. The theorem of zero set, I believe.
Okay.
Yeah.
I think the Stellen is like the place, right? So it's the theorem of the place of the zeros, something like that.
Yes, something like that.
Okay.
Yes.
Because it's the zeros of the polynomials.
Yeah. Yes.
Okay.
Oh, I have a question.
Yeah.
When was this done? When did they realize they can prove Nullstellensatz with model theory?
Oh, I have no idea the timeline. Maybe it's pretty. I'm just guessing. Maybe it's pretty recent. I believe. Okay. Because the point of view of model theory changes substantially in recent years. It changes to the point of view of algebraic geometry and number theory for the model theory. So I think it's pretty recent.
Oh, sorry. Yeah.
No, I just wanted to ask if he can give us a reference for that. So it's related to your question, Luis.
Oh, the reference? Yeah, I could give the reference. It's so it is. You can refer to the book written by let's see, written by Bruno Poisat, Poizat. Across model theory, Poizat.
ZET model theory.
A course in model theory, ZAT, a course in model theory.
The pause in model theory. Oh,
Yeah,
okay.
a course in model theory. Okay.
I cannot find it. Can you write it down in the chat, please?
I think I could.
Actually, could I chime in here a little bit? David Marker has some good stuff on this too. Maybe I could
Yes,
find a link to that. Poisat's book is famous, but it's also famously hard to read because he was a very poetic writer.
Who?
So
yes, you're right. Also, I found that book has some typos, so be careful. Okay, yeah. But that's the book I'm referring. It's Poizat, Poisat. Poizat, Poisat.
Should I stop recording?
It's up to you. I mean, yeah, we could. Yeah.
Okay.
But you're not going to post this one in the internet, Luis, are you?